Hey, Cal Kids, this is Mr. Beck. Today we're going to be talking about day 2 of second semester of Calc BC. And day 2 is going to involve working with differential equations, solving those differential equations, and then we're going to talk about 2 specific differential equations. One of them involves y prime equals ky, which turns into an exponential function. And then the other one's going to be y prime equals ky times 1 minus y, or something of that effect. And that gives us logistic equations. So we're going to start off with some basic differential equations. Now, differential equation that you see here is y prime equals 2x over y. Now, when it comes to differential equations, this is where y prime is an appropriate use of our derivative. So we're saying our rate of change does equal 2x over y. So that rate of change is with respect to 2 different variables here. Now, the very first thing that we're going to need to do, and it's kind of following the 5-step process I have up on top, change your y prime to dy dx. And then we're using what's called a separation of variable approach. Now, separation of variables is just that. We separate our variables, we bring all of our y stuff to one side, we bring all of our x stuff to the other side. So you can see here is I have y dy on one side and 2x dx on the other side. And then we integrate both sides. So when we integrate the left side, the integral of y dy is 1/2 y squared. The integral of 2x dx is x squared. Now, officially, we should have a plus c on both sides of the equation, but when you integrate both sides at the same time, it is okay to just put a plus c on one side of the equation, which is exactly what I did here. Now, this problem is either done at this point, or, and what you should notice in step 4 is if the question refers to anything about y equals f of x, or you see function notation, just like you see right here. It's what I added to this problem. You might not have it in your book, but I added this to your problem. If you see that, that means that you are to write y as a function of x. So 1/2 y squared equals x squared plus c. This, if we write it in its conic form, will look like this, where we'll have that x squared over 1. So hopefully you know that this is a hyperbola. This is a vertical facing hyperbola. But if we want to write it as a function, that's where we need to solve for y. Now, if we solve this for y, one of the things you'll first notice is I multiplied both sides of the equation by 2. If we do that, then what you should see here is I changed the variable. And this is very, very important because if you have 2 different variables that you're calling the same number, you're creating something that's not true, because 1 and 3 are not allowed to equal the same thing. So if c equals 1, c cannot equal 3. You have to give it a separate variable name if we, in this case, double it. So I have now changed this by multiplying both sides by 2. Then I take the square root of both sides. One of the things that you notice is we should have a positive or a negative square root, and that's because hyperbolas are not functions. So if you look at this hyperbola, it's not a function, it fails a vertical line test. So it needs to either be the positive square root or the negative square root if we're going to write this as a function. And that is where our initial condition kicks in. Since the y value is negative for the x value of 2, we are going to be taking the negative square root in this case. If y of c equaled positive 4, we would want the positive square root. So then we go ahead and solve for c1. We solve for c1 by plugging in the y value of negative 4. Then the x value of 2, we get c1 equals 8, which gives us our overall function y equals negative square root of 2x squared plus 8. Now, this is our particular solution. If we want to talk about what we did when it comes to slope fields, our particular solution is the solution that we have when we when we have a known point, and we use that known point to create the specific function. The general solution is what happens in this case right here. So that part is really the general solution. So just a quick recap, because I know that I spent a lot of time talking about how to go through just this one problem. Very first thing, excuse me, we use the separation of variables approach so that we get our x's to one side, our y's to one side, and we integrate both sides. And then we're left, in this case, once again, we have the general solution. So with the general solution, if we don't have any initial condition, we're done. We can leave our general solution in a variety of ways. But with the initial condition and also in this function format, together that tells us we need to know the particular solution, and the particular solution we solve for the C1. Now, the last thing that I want to talk about with this one specific problem is how does AP typically grade problems like this? Because when it comes to the Calc AB test, you're very nearly guaranteed that you're going to have a differential equation slash slope field problem on there. How does the AP grade this? Typically, these are about 5 points. So a normal differential equation problem is 5 points. The very first point, and let me go ahead and change colors on this. The very first point is, do you actually separate your variables? So to separate your variables, you must have this as dy dx. In fact, you get no points if you don't convert that y prime to a dy dx. So to separate your variables, you need both a dy, a differential of y, and a differential of x. You separate those, you get your first point. You integrate, you get your second point, and occasionally your third point if it's a 6-point problem. Then your third point comes from making sure you have that plus c immediately. If you don't have that plus c immediately, then you are done. You only get 2 out of the 5 points total. The fourth point is what they say if you use your initial condition. So if you notice what I did right here, I used my initial condition and I used it properly in the right context. So that's your fourth point. And your fifth point tends to come down to you have the actual answer. So to have that actual answer, and that's what I have highlighted in blue right there. All right, a lot of time that we spent on that one problem, but that's really kind of the explanation that we have for all of our problems here. Problem number 2, if you notice, there is no initial condition, so we just want to know the general solution for this. First step, put y prime as dy dx. Second step, bring all of our y's to the left, bring our x's to the right. Integrate both sides, and we're done. Now, this brings about a lot of the different integration skills. So what prompted me on this problem is I have natural log of y over y. So if u is the natural log of y, then du is 1 over y dy. That's why I took this approach. So I have I just have u squared in this case, which ends up being the natural log squared of y. Now, could I write this in different forms? Sure. Does it ask for a specific form? No. That's why I left it that way. For example 3, start off with, in essence, a word problem. Rate of change of p with respect to t, aka dp dt, is proportional. Now, if it says is proportional, that means that we have direct proportion, which is why I have k times my 10 minus t here. Then separate the variables, which is really not hard with this problem. Just bring the dt over to the other side, and then integrate both sides. And when I integrate both sides, both of these are actually viable solutions. The first one is kind of the approach that I tend to take. Not the approach I took right from the beginning. Very first time I learned and I actually taught calculus, I ended up doing more of the approach I just circled right there, where I said, okay, let's go ahead and integrate both, or integrate both terms with respect to t there. This tends to be the approach that I take now just because it's a little bit cleaner. Now both are the same. The constant values are different from each other, but both are equivalent as general solutions. Example number 4. If you notice, I did 2 steps in one. Really, and then separate and change my y prime to dy dx, and I separated my variables at the same time. Because I had a 1 over the square root of 1 minus 4x squared, I recognize, wait a second, this looks like an arctangent problem. So u is 2x, du is 2 dx. So there's my 2 dx, which I compensate with 1/2, and therefore I integrate into the arcsine of 2x. Now, one of the things to watch out for is our a value is 1, so we didn't have to worry about it. But remember, with arcsine, we don't have to put the 1 over a out in front. So it's just the 1/2 arcsine of 2x plus c. Problem number 5. Problem number 5 gets a little bit more complicated, and if you notice, we have an initial condition, therefore we have to find the particular solution. So first step, I did write y prime as dy dx, and I moved the x and the square root to the other side. Then I separated my variables, 1 over the square root of 1 minus y squared dy, the x over the square root of 1 minus x squared dx. So even though both of these look really similar to each other, we do have a big key distinction between the two. On the left side, we have a 1 over that square root. On the right side, we have an x over the square root. That means on the left side, we want the arcsine approach, where on the right side, we want to use the u substitution, where u is 1 minus x squared, and that's where the du, well, I guess I did have that written already in green right here. U is the 1 minus x squared, so du is negative 2x dx, and that's what I was looking for right up here. So the right side is a u substitution where u is what's inside the square root. But I integrated both sides, and this is where I'm using my particular solution. My y value is 1 when my x value is 0, and I'm able to get my c value. The arcsine of 1, if you guys remember, is pi over 2. This ends up being negative 1 right here, which I bring over to the left side, so c is pi over 2 plus 1. Then I went ahead and took this and brought it over. So the arcsine of y is that expression. And then because this is written in the function format, that's our implication that we are to solve for y, which is why I took the sign of both sides. Is that an ugly answer? Sure. At the same time, it's a definitive particular solution answer, which is why it's okay. Example number 6. du dv. So this time it starts off as du dv. So separate our variables, bring our u's to the left, bring our v's to the right. So on the left, we have 1 over u du, which is, boom, natural log. Don't forget your absolute value. On the right, it's v sine of v squared. So that's where what should come to mind is our u substitution, which, you know what, we really can't call it a u substitution because we have a u. So therefore, let's call it a w substitution, where w is v squared, dw is 2v dv. And if you see, that's the approach that I took on the right side, that our problem is really the sine of w, or the integral of the sine of w. So, which I did integrate. So 1/2 cosine v squared plus c, and use a particular solution. U is 1 when v is 0, so my constant is 1/2. And therefore, that is our particular solution, except function notation. Because it's function notation, we have to write u as a function. Now, either one of these are appropriate answers. One of the things that I do want to point out, this is something that's going to be kind of important as we go later on. If we have addition of exponents, we can multiply our bases, which is why it would be e to the 1/2 times e to the other portion. Well, it's not necessary here for us to do that. This is kind of showing some skills of what we're going to need for the future. Our last differential equation, put y prime as dy dx. Separate the variables, which in this case is bringing everything over to the right side, except for the dy. Now, this is a special case that what I did here was I moved that 2 as an exponent out in front, and then I reduced. But we have to watch out that that does change the domain if we're not careful, because the domain of the problem as it's written is everything but 0. The x is everything but 0. So don't forget to include those absolute values. And then if we integrate integrate both sides, you'll see I have 1/2 natural log squared. This is similar to the integration we did earlier. And with our particular solution, when x is 1, y is 2. That allows us to find that our c value is 2. And our c value, as I said, is 2. Therefore, that should be a plus 2. All right. Excuse me on that cough. So number 1, did we separate our variables? Number 2, did we integrate both sides properly? Number 3, did we have the plus c initially? Number 4, did we use our initial condition? Number 5, do we have the actual solution? My guess is on an AP test, this would probably be just a 4-point, where they wouldn't necessarily give you the initial condition point, just because pretty much there's no work to be done after you plug it in. So probably 4 points on this problem. But anyway, so there is the last of our practice. So now let's get into exponential growth of the form y prime equals ky. If we have y prime equals ky, that should immediately tell you that you have an exponential function as a solution. Now, where you have these kind of problems in real life, I like to think about monetary value. So When you invest money, you get interest off of the amount of money that you have in there. What this means is the rate of change, and in this case, the interest of your money, is dependent and the rate of change is dependent upon how much money you actually have in there as well. So it's the rate of change and, or how about the interest rate and the amount of money that you have in there. So if you take 8% of a value, then you're going to add that 8% onto that value, and you keep doing it over and over and over again. What you're seeing is y prime is going to be dependent upon the actual dependent variable. So our rate of change is based off of the dependent variable. That's why it's an exponential function. This is such an important theorem that you really need to know, because it's your job to connect y prime equals ky turns into an exponential. I've seen lots of AP multiple choice problems where they say, okay, y prime equals 3y. What kind of function does it represent? Your choices are really like exponential, quadratic. Can't think what the other ones are going to be, but they have lots of different choices there. Usually what I've seen is you have two different exponential functions, and that's where this C is your initial condition. So the initial condition they give you, you could put that in place of that C. So anyway, this is such an important theorem because it's your job to recognize that kind of differential equation turns into exponential. I think I said that once or twice, right? So here's our proof. So with our proof, we're again taking the separation of variable approach, bring our y's to the left, bring our non-y's to the right, integrate both sides, natural log of the absolute value of y, and then take e to both sides. So when I take e to both sides, one of the things that you should notice is e to both sides, we can drop the absolute values, and that's because if we're taking e to both sides, we know that y has to be a positive value. So we don't have to worry about it. The only way it would not be positive has to do with all of that information and solving for the particular c. But if you notice that exponent that I just highlighted, then we have addition of that exponent, which means we can multiply those bases. And e to the c1, we can just write as a generic c. So this proof is not necessary to do over and over and over again. If you don't make this connection right away, you'll find you're going to be doing that proof many, many times. So it's just easier to say we know what's going to be the result. So examples 8 and 9 are really just both done to highlight that this y prime equals k times x, or in this case t, or this one is y prime equals k times y. So one is the independent variable, that one's the independent variable, this one's the dependent variable, but and that shows you that we have two different types of functions that result. So when we're dependent on the independent variable, then we integrate both sides, and you'll see it turns into a quadratic relationship. And then that initial condition they give us is 0, 10, means that our c value here is 10, versus y prime equals ky. We know that that immediately goes to the exponential function, where the k value is the coefficient there. Becomes the exponent, goes into the exponent. Anyway, our initial condition, that's 10. So we could spend more time doing work on that, but it's really to highlight just the change in variable versus the independent versus the dependent gives you an entirely different equation, which hopefully does make sense. Examples 10 and 11 aren't necessarily calculus. They're just a lot of pre-calculus skills to remember. So when it comes to problem number 10, what we're doing here is our goal is to find the exponential function that goes through these two specific points. So this turns into a, hey, let's plug in those points and figure out what the system of equations looks like. So we plug in both points. I tend to solve for c on the smaller exponent, because when I do that, then I get that relationship there, e to the 4k over e to the 3k, which is just e to the k, and then I multiply both sides by 2. When I did that, I can now solve for k. K is the natural log of 10, which then I go back and solve for c. So 1 over 2 e to the 3k. And then if you remember, based off of your arithmetic, 3 natural log of 10 is really the same thing as natural log of 1,000. And e to the natural log of 1,000 is where we get just 1,000. So 1 over 2 times 1,000. Then I go ahead and put that all together. Now, officially, if you remember, e to the t natural log of 10, we could rewrite that as e to the natural log of 10 to the t power, which is how I got the solution right here. The problem does ask us to do what's in blue rather than what's in red, but I do want to say what's in red is a viable solution if I just generically ask for an equation. But I did ask for y equals c e to the kt, so what's in blue is more appropriate. Example number 11 is very, very simple, similar to number 10, except for we're already given the initial condition. We have 3 grams to start with, so boom, we could write it that way. Radioactive decay, the reason why exponential functions will model radioactive decay is because the rate of change is always based off of how much of the substance is there. So what's happening is all the radioactive isotopes are leaving at a certain rate, and so that leaving is based off of the amount of substance that's there. So hence that's why it's y prime equals ky. So I said its half-life is 5730 years. So after 5,730 years, we know that we have 3/2 of a gram as opposed to just 3 grams because it's half-life. So then I solve for k. Now this k value that I solved for, I went ahead and plugged it back in to the equation, and I also plugged in 1,000 because that's what our problem is directing us to do. Please be very careful that you must, if you're ever using that value, don't round until the very end. At the very end, we do round to 3 decimal places, but if you take that expression that I have, the 1 over 5,730 times the natural log of a half, if you rounded that as a decimal there, you end up getting in trouble. On example number 12, this would show you where you could potentially get into trouble. If you notice, we're doing really the same thing. Our initial condition, when t equals 0, w is 5,000, so I knew that this is going to be 5,000 e to the kt. How did I know it was going to be that form? The rate of change is w is proportional to w, so that's my dw dt is k times w. So our setup pretty much dictates that. And rather than having to do all the work, I know that I could turn it into that c e to the kt. Now our c value we're given. To find the k value, then we have to use our secondary point, and that's what I did here. E ends up being the natural log of 19 over 20, which then I have to say what's the value w when t equals 5. That's where I have this. Put it all together, and I get 3,868.905 because at the very end only, that's where we round. Then we move on to logistic equations. And logistic equations, this problem that I have here, y prime equals y times 1 minus y over 400 is supposed to represent it. So what I did was I began my separation of variables approach. I did factor the 1 over 400 from it. And in doing so, I then brought everything to the left side where I have just my dt to the right. And in doing so, this creates, how do we integrate this? Well, to integrate this, we have to go through partial fractions. So break apart my denominators and solve for a, solve for b, which if we do if y is 400 and if y is 0, what it turns out are both a and b are 1. That makes life happy, which is where I went to this step. And now I integrate both sides. Be very, very careful. Most students tend to forget that the integral of the 1 over 400 minus y, if you say u is 400 minus y, then du is negative dy. So that's why it's going to be minus the natural log of that. Put it all together. And then I take e to both sides, and in doing so, I have this statement right here. So one of the things that I do like to see about this, especially since we just talked about y prime equals ky, if we have y prime equals ky versus y prime equals ky times 1 minus y in essence, what that allows us to focus on is it's the ratio of those two factors, the ratio of those two factors, that's where we get the exponential function. So it's the ratio that becomes exponential. And in doing so, then we solve for y, we multiply both sides by the 400 minus y, distribute, bring all the y's together on one side, solve for y by dividing. Now, then it's at this step right here that if I divide both numerator and denominator by c e to the kt, then I get what is our common logistic function. So what this allows us to do is, if we know all the individual pieces, it allows us to skip from beginning to end to say that differential equation is always going to turn logistic. And in the form that it currently is, that is our carrying capacity. If you're going to talk about the logistic model. And if you notice, the K value I have here really is 1. That K value translates into the 1 plus V e to the negative KT in our logistic function. So knowing all those pieces allows us to just skip from beginning to end so much more efficiently. Now, I love doing all the partial fractions and all the work in between, but that might not be your cup of tea, and I'm not going to be on that one. So it's about recognition. So that recognition, I tend to look at it really from that form as often as possible. However, this form is honestly how the last problem started. So if we know that, then we know that it turns into the logistic model. So where the other one was theorem 5.1, I think this actually has a theorem name in our book, or a theorem number in our book. But I forgot to put it on the notes. Sorry. A couple things about logistic functions. If you notice that we have this concave up until we reach half of the carrying capacity, and then this concave down all the way to the carrying capacity. I see lots of problems asked about this, that the rate of change is increasing here. The rate of change is decreasing here. That rate of change is concavity, or increase and decreasing is our concavity. But knowing that it's half the carrying capacity that gets us there is going to be very, very important for you guys to know. And then we have our first problem. State Game Commission releases 40 elk into the game refuge. So our initial population is 40. So T equals 0 is 40. After 5 years, the population is 104. This is kind of similar to the problems that we just did, where this is going to help us set up our equation. Then this is going to allow us to find our rate. Now, if you notice what I scratched out is the commission believes the environment can support no more than 4,000 elk. That's great and all, but it's kind of unnecessary information because that is what's given to us in the differential equation here. So we should know that. Now, all of a sudden, I popped up, boom, there is my logistic function. It's like, wait a second, how did I come up with that so quickly? Because our carrying capacity is 4,000, and we're then going to use the rest of the information to figure out what that rate is. If they gave us the rate here, we could have immediately plugged it in, but they didn't. What they did give us was after 5 years. So that's where I plugged in, first I actually plugged in 40 as my initial population, and e to the 0 is 1. Solve for b to get 99. Now I'm going to be using that second piece of information after 5 years. So e to the negative 5k. I have 104 as my population. Solve for k. Now please keep in mind that is a really nasty number. If you use your calculator, don't forget you can store that value in your calculator. Just store it. That decimal approximation is 0.194. So if I was done, and that's all I needed, that's going to be my function where I can put my 3 decimals there. But if you look at part B, we have to know what's our elk population after 15 years. So I wrote this as K representing that whole expression. And I was able to say I have 628.538 elk, which obviously is either going to be 628 or 629. So rounded up or rounded down based off of directives. In this case, probably rounded up just because usually questions like this say to the nearest elk. Now, what's our limit as t approaches infinity? That would be 4,000. And I really knew that right from the very beginning because that's my carrying capacity. Other questions that I could ask is, at what time have I reached half the carrying capacity? Which most of the time is really not as blatant as that. They would say, where is the rate of change of elk growing the fastest? AKA, that would be your half your carrying capacity. So if they asked you graphically, where is this concave up versus concave down, you could find this algebraically by setting our population equal to 2,000 and solving for t. And then our AP problem here. I took my differential equation, which I immediately recognized that this is logistic. What I did was I factored out the 2 so that I had the 1 minus p over 10,000, and that allowed me to determine that our limit as p approaches infinity is 10,000. So hopefully you enjoyed today's notes, and I enjoyed sharing that with you, and I hope you have an amazing day.